class. This is CSE-4600, Section 1, Week 11, Spring 2025. Alright, so as you may know already, you have your second project that is due next week. For us to ease into our last topics for operating systems, we're going to begin on a brief discussion on files and file systems. So, there are three abstractions that the textbook discusses. The first abstraction is that of a running program. A process is an abstraction of a running program. It contains the values stored in the CPU. Rather, the values stored in the CPU's registers. By storing that information in what's called a process control block, we can save the state of a running program so that if we need to run a different program, we just unload the program and load the next program. That's it. The second abstraction is that of memory. Every process has its own address space, independent of that of any other process, unless we're sharing memory. The idea behind a address space. To enforce that, we use virtual memory and paging. We break up physical memory into equal-sized page frames. Similarly, the address space of a process. And every process's address space, they start from 0 and they stop at some maximum value. Every process's address space is broken up into pages. When a process needs to run, that process's pages are loaded into memory, but we only need to load the ones that we need. Yeah, even if you paid for the whole program, it's not feasible to use the whole program. Not all at once, at least. So, to be space efficient, we just load only the pages needed to run the program. And if we need to load other pages, we just load them as needed. If we have idle processes, then those processes' pages are unloaded into memory and they're put back on secondary storage. When the process needs to run again, we just load that process back on the CPU, reload all those pages that we need, and the process will just run like nothing ever happened. Our third abstraction is a file. We have a good idea of what a file is, but not so much the nitty-gritty details, such as how is a file stored on a disk. We're going to begin our discussion on what a file is. So all of this is going to be a recap from Tuesday. In case you missed it, I'm just going to recap it here. So main memory is also a place in which we can store information, but it's not the best place to store lots of information or information for the long term. The problem is this: main memory is way too small. Also, main memory is volatile. When a process terminates, its memory goes bye-bye. So all the memory that process had used gets reallocated to other processes. So any information that process had, it's gone. And more to the point, main memory is volatile. So when you shut down the computer, even if you can have that information persist after a process has terminated, once you power down the computer, that information goes bye-bye. Third, multiple processes may need to access the same information. So we want this information to be independent of any process. Yeah, we can do memory sharing, but what if you had to do memory sharing between two programs whose developers have no idea who they are? So really the solution to this problem of not enough space in main memory is volatile. We need some way for processes to access the same information. We solve that issue by saving our information into files saved on a hard disk drive or a solid state drive. We are mainly going to concern ourselves with hard disk drives. There are some key differences between hard disk drives and SSDs. Mainly, it's faster to read information from an SSD. There are no moving parts. There are some challenges as well, such as the NAND flash memory chips that make up a non-volatile memory device can only withstand a certain number of reads and writes before that chip becomes unusable and you cannot read or write to it anymore. So when it comes to non-volatile memory devices, you gotta wear down the whole device evenly so that no one module is too worn down than any other module. For our purposes, we're going to conceptualize a disk as a linear sequence of fixed size blocks. And this is for good reason. The earlier methods of storing information on computer systems was magnetic tape. As I said, as I may have mentioned, there are three abstractions. So the first abstraction was the process, an abstraction of a running program. A process contains the values stored in a CPU's registers. By saving that information in a process control block, we can basically save the state of a running program so we can let another program run. Virtual memory is another abstraction where each process has its own address space, independent of any other process. By cutting up memory, physical memory, into page frames, and a process's address space into equally sized pages, when we run a program, we just load the parts that we need, and if the process goes idle, we just unload all those pages, put them back in secondary storage, and if it has to run again, we just load it back, load the values for the registers from that process control block back onto the CPU, take the necessary pages to run the process take it back from the disk and load them into memory, and the process will run just fine, like nothing ever happened. A file is another abstraction. It's a logical unit of information created by a process. So a process does work. It does some computation. It has results that it probably needs to save to a file. Your typical disk may have thousands, maybe even millions of files. Each file is independent of every other file. Each file takes up some space on a disk in the form of blocks. Kind of like how pages of a process's address space take up page frames in physical memory. In fact, the way that files are stored on a disk is not unlike how processes are stored in memory. In memory, you have processes cut up into pages, and they are going to take some number of pages. They are going to occupy some page frames, not necessarily in the same place. The same is true with a file. A file may be a sequence of blocks, not necessarily all in the same place, where a file starts at one block and then proceeds to the next block, and then it may proceed to the next block after that at some other location. That's just one of several ways files can be stored on a disk, by the way. So, kind of like how processes grow and shrink in memory, a file can grow and shrink on a disk. The only difference between processes stored in memory and files stored on a disk is when you turn off the computer, everything in main memory disappears, but the information stored on a disk persists. It stays on the disk long after you've turned off the computer. Files are managed by the OS. How they're structured, named, accessed, used, protected, implemented, and managed are all major topics in operating system design. And the part of the operating system that deals with files is called the file system. So, as I said, a file is an abstraction mechanism. It provides a means of storing information on the disk with the ability to read back from it later. This is done in a way to shield the user from the details of how and where information is stored and how disks actually work. By that, I mean, if you want to create a new file, all you gotta do is open some program, create a new file. That's it. Or in some cases, you can just right click and create a new file. Maybe you can create, for example, a new text file. That's it. No specifics on where do you want to save the file, apart from what folder you want to save your file in. There is nothing about this process, nothing about the process of making new files involves telling the user what block do you want to save this file in. For example, when we create a file, we give it a name, of course. When the process that created the file terminates, that file persists and can be accessed by other processes by its name. The names that we give to files, the rules for that may vary from system to system, but generally, you can use alphanumeric characters. Operating systems may have differing minimum and maximum lengths. File names can be as little as 1 character and could also be as high as 255 characters. You could probably even use Unicode as part of your file name at this point. I'm not sure if you can use emojis as part of a file name, but I would not be surprised if it were possible to do that. Some operating systems, such as MS-DOS, are not case sensitive. Most modern systems are case sensitive. So if you spell homework in all caps and homework capital H, or homework lowercase h, or homework mixed uppercase and lowercase, in MS-DOS, those are all the same file names. But in most modern systems, it'll likely be, those are all different file names. Windows 95 and 98 both used a file system called FAT, more specifically FAT16. Windows 98 introduced an extension to that called FAT32. All Windows versions after that, starting at Windows NT, and then XP, Vista, 7, 8, 8.1, 10, and 11, they all support FAT, but at this point, FAT is obsolete, so all those Windows versions support the newer NTFS file system. I believe FAT stands for File Allocation Table, and then NTFS, New Technology File System. New Technology File System. There are more details regarding FAT and NTFS in Chapter 12 of the book, by the way. Many operating systems support a two-part file name, where we have the file name, a period, and then a file extension. The file extension indicates that a file is meant for a specific purpose, or more commonly, it's used as an indicator. We use the file extension commonly as an indicator as to what the file is for, and in some cases, what programs are meant to open the file. If you have a .c file, that's going to be a source code file for a C program. CPP is for C++. File types such as GIF, JPG, JPEG, BMP, PNG, TIFF, those are file types that represent some sort of image. And they all have their differences. So for example, JPEG and PNG are two of the most common file types for images, but they have their different purposes. They have their own use cases. JPEG is used for cameras, and they store information in a lossy compression format. That means if you zoom in really close into a JPEG, you're gonna see these little squares. Those are called JPEG artifacts. PNG supports a lossless compression format. That just means you will not lose as much. That means when you compress this file and the information in PNGs is compressed, it's compressed in such a way that we don't have compression artifacts. Also, PNG supports transparency, which makes it good for situations where you want transparent images. There's also other file formats such as MP3 and .wav. Those are formats used to represent sound information. MP4 is for video information. .ogg is also another file format used for sound as well. There's also .pdf, which is used to represent online documents. Some file types are exclusive to certain programs. For example, .ppt and .pptx are PowerPoint files used mainly by Microsoft, although there are some other programs that can read .ppt and .pptx files. Similarly, .blend, that is the file type for a 3D modeling program called Blender. So a .blend file contains information about the placement of vertices in a 3D space, and also what textures are to be mapped onto those faces. Blender, the program, works with .blend files, though there are other programs that can parse the information within a .blend file, such as Unity. Yeah, Unity, the game engine. You can import .blend files directly into Unity. So, yeah, the file extension of a file name it's an indicator as to what purpose this file is for, and to an extent, what programs can open the file. Some files lack a file extension altogether. When you compile a program on a Unix machine using, say, GCC or G++, you're going to create an executable that lacks a file extension. On a Unix machine, that is an executable file. On a Windows machine, you can tell what an executable file is by seeing whether the file extension is .exe. For some systems, such as all Unix systems, file extensions are just suggestions. The system does not know or care about what the information is or what it's even for. They're just there as a human convenience. So something like the sprite sheet here, let's say it's called spritesheet.png. It indicates that it's an image, but as I said, some operating systems don't care. As far as the operating system is concerned, all it knows is that this is a file that contains a sequence of bits that mean something, but that meaning is lost to the OS. The OS doesn't care. So if you read that PNG file, it's gonna look like this, and good luck reading it. I'll get more into the details as to what this even means in a little bit, but you can parse some meaning by the fact that the first line says PNG, and the next few lines after that says something like softwarepaint.net. That indicates that this file is a PNG that was edited in paint.net. Okay, so I'll get into that in a little bit, by the way. Files can be structured in one of several ways, and the most common ways are as a sequence of bytes, a sequence of records, or as a tree. The simplest way to structure a file is as a sequence of bytes. Here, the meaning of those bytes is imposed by the program that uses it. The OS does not know or care about what the bytes mean. But on the other hand, having the OS treat files this way gives us the maximum flexibility as to what we can do with the file. User programs can put anything they want and name them whatever is convenient to the programs. So as I said, this sprite sheet is nothing more than a sequence of bits that happen to encode visual information. An executable file is nothing more than a sequence of bits but those bits all encode instructions that can be run on the CPU, among other things. A TXT file encodes a sequence of bits, but likely those bits are going to be ASCII characters, or possibly even Unicode characters, that, of course, encode textual information. So I have a program called Notepad++. You can do this with regular Notepad, by the way. You can open a .png file, for example, using Notepad, and you're gonna get some gobbledygook that looks like this. If you do this with an executable file, you'll get similar gobbledygook as well. All versions of Unix and Windows use this file model, where a file is nothing more than a sequence of bytes. What the bytes mean depends on whatever program is working with the file. The next step up is a file that is a sequence of records. Each file is a sequence of fixed length records, and those records have some sort of internal structure. When we do a read or write operation, it works on one record at a time. There was a time where computers would only display up to 80 characters in a line on the screen. At the same time, there were line printers that would print up to 132 characters at a time. If you had a program that had to save files onto the disk, well, back then it would have been magnetic tape or something like that. Because the storage format was meant for line printers, the information saved by a program would only take up 80 of the 132 characters per record. So basically, these records were holding one line of information at a time. How much is a line? It's either 80 characters or 132 characters, depending on whether this is information that was from the screen or information that was meant to be sent to the printer. So if it was 80 characters, that means the other 52 characters are just spaces. So that's what I mean by saving information at the record level. So these are records of 132 characters each that can either be 80 characters or 132 characters, depending on whether it was meant to be printed to the screen or printed on the line printer. The third type of file structure is a tree. So each record of a tree may not necessarily be the same length, but each record contains a key field and is fixed position in that record. We sort the tree by the key, and the basic operation is not so much to find the next record, although we can do that. Rather, it's to find a record that has a specific key. New records are added by the OS, not by the user, and this is used on some mainframe computers. There are two main file types that we typically work with, though Unix has two more file types. The first type of file is just the regular file. It's just a file that stores information. There is another kind of file called a directory, also called a folder, and that is used to maintain the structure of a file system. Unix systems have two more special file types. The first one is called a character special file, and the other one is called a block special file. A character special file is like this. If you have, say, a speaker and you want it to output sound, you would, for example, okay, so if you have a character special file, and maybe not a speaker, but rather you are trying to print to a printer, basically you write to this special file as though you're writing to a regular old file. That information is then transmitted to the printer, and it just prints out the document. So to print out a file is gonna be no different than, say, writing to a file. The same is true of block special files. So character special files are related to I/O. Block special files are meant to model disks. So if you want to write to a disk or write to a printer, it's going to be no different from, say, it's going to model writing to those kinds of devices like it's going to be writing to a file. Regular files are either ASCII or binary. If they're simply ASCII files, then there's just going to be lines of text. Each line ends with a character turn, which is typical of older Mac operating systems, a line feed, which is typical of modern-day Unix systems, or both, which is typical of Windows. Lines can be all of different lengths. The advantage of ASCII files is how whatever it says in the file is how it's gonna read when you print it out. It's also easy to connect the output of one program to the input of another program, such as with a shell pipeline. Binary files are, well, not ASCII files. These are files that store binary information. If you try to read, say, a PNG file in a text editor, it's gonna look like random junk. The meaning of these characters is not only lost on the operating system, but also lost on the user, because, well, good luck reading this, but it encodes information that certain programs, such as Paint.net, are able to parse this information and make sense of this information. An executable file, as I said, is also a sequence of bytes. But at the beginning of that executable file is a magic number that identifies the file as an executable file so that the OS can run the file. The magic number is just one part of many parts that make up the header of an executable. Other parts include how large is the text size, how large is the data size, where in the program does executable code start, and that is just one part of many other parts that make up an entire executable file. We have the text, we have the flags, we have relocation bits, and we also have the symbol table used for debugging. There's also another type of file called an archive file that's typical of Unix, much like the executable in, say, the PNG from before. It's all in binary data, so if you're to try to edit it in a text editor or print it out, it's gonna look like gibberish. If there is one file that an operating system must know how to read, it's likely going to be the executable file. Imagine you're a game developer and you wanted to save files in a special format. Let's say you have a game. Let's call it, I don't know what to call this game, but let's say the save file for this game is called .savefile or .gamesave. Because the operating system does not know or care about what goes in a file, we can just put whatever we want in the file. And for the case of our video game, we can put game save information. Where is the character in the world? What achievements has the character achieved? What is in the character's inventory? Is the character under the effect of any potion effects? What equipment is the character wearing? So we can encode that in any way we want, as long as the game itself. And the game, it's basically just another program that can... The video game in question is just nothing more than a program that can read from a file and write to a file. It's just that it's encoding stuff in a way that only it can understand. So let's imagine the reverse scenario, where if you wanted to save your game information in your video game using your own file type, .gamesave, wouldn't it be annoying if you had to wait for Microsoft to support that file type? If that were the case, maybe the alternative would be to save to a text file, but that assumes that the system can even understand what a text file is to begin with. So if there is a file type that all operating systems must be able to understand, it's gonna be at the absolute minimum its own executable file. So some systems can recognize more than one type of executable. So some systems can recognize more than one type. Early operating systems only ever had one form of access, and that's sequential access, because we used to save files on tape. Not unlike this, but way, way larger. Like 1 foot diameter reels that you would carry from to and from a tape reading machine. Files, either as a sequence of bits or a sequence of records, can only be read in sequence. We can only read it in order, so from the beginning to the end. We cannot skip around. Well, we can fast forward or rewind the tape, but how do we know we've reached the desired spot yet? And the idea behind saving information as a sequence of bits was convenient because, again, back then all we had was magnetic tape. Once hard disk drives, and later on solid state drives came around, we would then get another means of access, random access. Here we can read bytes or records at any location in any order. And many applications require random access. Say you made reservations for an airline. If you want to access that information, how annoying would it be if you wanted to access that information, but you had to wait for the 5,000 other reservations that have been made before you? This is why we like random access. It's not random, but it's faster than stepping through all the thousands of other records that have been made before it. There are 2 methods that we can use to specify where to start reading. The first one is by just using the read operation. The read operation gives the position in the file to start reading at. The second one is to use another operation called seek. So seek is an operation that allows for random access. What seek does, in a file, there is a pointer that points to the location to read from next or to write to next. What seek does is it changes that pointer to point to any location within the file. When we call seek and we change the pointer, it changes where we can read from, and then we can call read and start reading from that new location. Both Unix and Windows use this method. And now we get to file attributes. Every file has a name and data, but there's more information than just that. We call this extra information file attributes, but it's sometimes called metadata. And this can include, for example, password protection. Is the file password protected? Who created the file? Who currently owns the file? Who is allowed to read the file? Who is allowed to write to the file? Who is allowed to execute the file? So, password protection, read, write, execute bits, they are called RWX bits on a Unix system. There are also flags that specify whether a file is read-only or has been recently archived. There are other attributes such as when the file was made, who last edited the file, when was the file last made, and also how large is the file, and what is the maximum size the file is allowed to grow to. Not all systems will have all of these attributes, but all systems will have some of these. And as I said, and again, some of these are pretty self-explanatory, such as, is the file password protected? Who made the file? What is the protection bits on it? Who made the file? Who made the file? When was the file made? Who last edited the file? When was the last change made? And how large is the file? As I said, files exist to store information that we can retrieve later. How that's done varies from system to system, but we're going to discuss the most common system calls related to files. So, we can create a file, obviously. this creates a file with no data in it. We can delete a file. When a file is no longer needed, we can delete it to free up space. How is a file deleted on the disk? So you would think that when you delete a file, the system goes in and scrubs every last bit of information from where that file was taking up space. So if a file takes up, say, some number of records on the disk, you would think that the operating system would go in and scrub every last bit from those records that the file used to use up, and then those records can then be used for new files. That's not quite how it works in most systems, though. I like to think about it as this. Imagine a city with a weird ordinance that says a house is a valid structure if it has a driveway connecting it to the nearest street. Demolishing a house is simply demolishing the driveway. Once that driveway has been demolished, it is free real estate for anyone who wants to redevelop the area. So you can have this town full of, like, half-cut houses and new buildings next to them. And that's not a bad representation of what happens inside a hard disk drive. Another way, and this is probably the more simple way to explain it, deleting a file is like taking the table of contents from a book and ripping it out. The information is still there, but it's harder to access. So if you really want to delete the data, well, I'll leave it to you to think about how you would really delete your data. But if you want to do it physically, we can physically destroy the hard disk drive. But if we want to save the drive so that someone could, for example, reuse it, I guess one way to do it is to take the information in that file, open the file, replace it with garbage information, and then delete the file. So when that file is deleted, any last trace of the original information is going to be overwritten with random garbage. You can imagine that this kind of information destruction would be very, very, very valuable to the US government. I'll leave it to you to contemplate as to why that is the case. On the other hand, if you accidentally delete a file, because when you delete a file and it goes to the recycle bin, that is a purgatory where files are either deleted, and I say deleted in a loose sense because it's not really deleted, it's still there, but it's just harder to access, or we can choose to revert that, go to the recycle bin operation, and it just becomes a regular file on our system again. When we delete a file, there is a data structure on the disk that says where to find that file on the disk. When we delete the file, that entry in that data structure is just removed. So the information is still there, but we can't get to it. This is what I mean by taking a book and ripping out the table of contents. The information is still there, but it's harder to access. But in the unfortunate event that you have a hard disk failure, or you accidentally delete a file that you didn't want to delete, there is still a chance to get it back. There are tools out there that will do exactly that. It will search your directory structure for any lost information, and if it's there, you have a chance to get that lost information back. Alright, so that's my spiel on creating and deleting files. There are more operations than just making and deleting files, by the way. The first one is called open, which is pretty self-explanatory. Open a file before a process can use it. And once a process is done, we close the file. Oh, why do we have to open and close a file, by the way? And the reason for that is pretty simple. That data structure that I mentioned, where on the disk it lists what files are on the disk, for us to find the file, we have to search that directory structure to find the file that we want. Once we find it, to make it easier to access the same file again, we take that information and store it in a special data structure managed by the operating system called an open file table. So this table contains information on what files we want to access right away. The open system call finds a file with a specific file name. It finds that information from the directory structure and saves that information in the open file table. When we call open, it returns a non-zero integer value that represents where to find that information in the open file table. When we work with files in say C or even C++, open returns what is called a file descriptor, or in other systems it may be called a file handle. We use that file handle or file descriptor to represent the file that we are working with. And that file is just a number that is used to access an entry in the open file table. And that entry is just the directory information that we fetched from when we first searched that disk for that file. Close. When we call close, we then take that entry and just remove the entry from the table. That signifies, hey, we're done with the file. We don't need to save this information anymore. We can just free up that space so we can use it for other things, like opening other files. So that is what happens with open and close behind the scenes. It just makes it easier to access a file that we are working on. Read is another system call. We read bits of data from a file and store it into a buffer. Actually, we tell the system, in the system call, we specify some number of bits to read from a file and store it into a buffer. The read system call then returns the number of bits that was actually read. So if we have a 4096-bit buffer, and there are like 3000 bits in that file that we were reading, we call read, we pass in a buffer, we pass in a file descriptor, and we pass in 4096 that says we are trying to read 4096 bits from the buffer. Oh, my bad. It's bytes. My mistake. So, we pass in a buffer, we pass in a file descriptor, we pass in the number of bytes to read. So, we tell, using read, we tell the system, read 4096 bytes from the file and store it into the buffer. If the file was smaller than 4096 bytes, it will return the number of bytes it actually read. And if that value is 0, it means there was nothing in the file to begin with. And if it's somehow negative, that means something went wrong. Write is the counterpart of read, where we pass in a buffer, we pass in a file descriptor, and we pass in the number of bytes to write to a file. This also returns the number of bytes that we wrote to the file. Append is a restricted form of write, where we write information to the end of a file. If a system does not have a separate append operation, we can replicate it by calling seek to move that read-write pointer to the end of a file, and then we call write. That means we also have an operation called seek. This is the operation that changes where the read-write pointer is pointing to in the file. Again, seek is how we enable random access. If we call seek to change the location of that pointer to anywhere in the file, we have random access. And then we can call read to read from that location, or we can call write to write to that location. Get attributes and set attributes. Some systems need to read file attributes to do the work. Some attributes, we can change it at the user level. And finally, rename. Sometimes we want to rename our files, and we can just simply change the name of our file. If a system does not have a separate rename operation, then we can replicate it by copying the contents of an existing file to a new file with a new name, and then deleting the old file afterwards. And that is where section 1 mostly stops. I'm gonna get to section 2 right now. So section 2 of chapter 4 this is part 2. This is gonna begin with an example program that reads from a file and then writes to a different file. So everything I was talking about regarding those system calls, we're gonna see a demonstration here. So the following is a crude but short example program that opens a file, reads from it, writes to another file, and then closes the two files. So this is a program where if we want to run it, we type into the command line copy file, the name of the source file, and then the name of the destination file. The source file, that's the file that we are to read from. The destination file, that is the file in which we write the copy to. If the destination file does not exist, the program creates it. If the destination file already exists, the program just overwrites it. At the start of the program is a bunch of boilerplate code that, among other things, includes these two macros. The first one specifies that our buffer size is 4096 bytes. The other one specifies protection bits for our output file. The main function, notice how there's stuff inside the parentheses? That's because the program is set up to accept command line arguments. So when we type in our command, copy file abc xyz, where abc is our source file and xyz is our destination file, that information is going to be stored in a character array called argv. argc just tells us how many arguments have been entered in this way. So argc specifies, as I said, it actually specifies how many strings were in the command that ran the program. So if we type in copy file abc xyz, there are 3 strings. That is copy file abc and xyz. abc is the source file name specified by argv1. xyz is the destination file specified by argv2. So, argv2, as I said, that's just a pointer to an array that contains those strings. So copy file abc and xyz. Next, there are 4 integer values and our character buffer. So those 4 integer values, the first 2 are gonna be for our 2 file descriptors. So file descriptors are integer values that represent our input file and our output file. When we open the input file, we're gonna get a file descriptor that we can use to write to our. No. When we call open and pass in argv1, we get a file descriptor that we can use to represent the file for when we read from the file. When we call create, and create is spelled C-R-E-A-T for some reason. When we call create and pass in argv2, that is our destination file, we get a file descriptor for that file, and we can use that for when we start writing to it. The other 2 ints are read count and write count. Those specify how many bits were read from the source file and how many it specifies how many bytes were read from the source file and how many bytes were written to the destination file. Also note that this program is meant to run with argc equals 3. If that's not the case, then it's gonna exit with an error code. When we call open, here we call open and pass in the file name specified by argv1. We also specify a read mode called read only. when that system call executes, it returns a file descriptor, as I said. And this is a non-negative value. If it is negative, that means something went wrong with trying to read the file, and the program closes with an exit code. Similarly, we can pass in a file name into the create system call. We can also specify the output mode, which has already been specified for us using the macro here. So much like open, create returns a file descriptor that we can use to represent the file when we start writing to it. If the file descriptor is also negative, specifically if it's -1, it will return -1 if something went wrong with trying to open the file, with trying to create the file. If that's the case, then the program will just exit. Now we have an infinite loop where within that we read a block of data from our input file, and then that block of data that we read, it's stored in a buffer. Then we take that information in the buffer and we write that to our output file. If we call read and read returns 0 bytes, that means we reached the end of the file. There's nothing else in the file to read. Alternatively, if it's negative, it means something went wrong with trying to read the file, and we also exit. So, we call read to read 4096 bytes from the file and store it in a buffer. Then, we take that stuff in the buffer and we write it to our output file. So, read count, that is the number of bits that we read from the file. When we write to our output file, we also must specify the number of bits, the number of bytes to write. I'm mixing up bits and bytes today. So when we call write, we specify our output file using our file descriptor, we pass in our buffer, and we pass in the number of bytes to write. So write also returns the number of bytes it had actually written. If that count is somehow less than 0, that means something went wrong and we had encountered an error. The program closes with an error code. So, this infinite loop will break once the read count is 0 or worse, negative. Once that's the case, the program breaks out of that loop, and finally we can close our input file and our output file. If the read count was 0, then the program exits normally, but if it was less than 0, then there was an error with trying to read from the file, and then the program exits with an error code. So that's our example program. Although this is a Unix program, the basics of what happens here also apply to a Windows system. And now we talk about directories here. File systems have directories, also called folders, and their purpose is to enforce organization. Folders are files, but instead of storing information, they're used for organization. We're going to look at how we can organize directories. And the first one is just have one level of directory. This is a single level directory. This is the simplest possible directory structure you can ever have. You get one folder and that's it. The advantage to this, although the obvious disadvantage of good luck trying to organize anything, although we have that obvious disadvantage, the advantage of a single level directory is that it's simple to implement, and as long as you don't have thousands of files, it's pretty easy to search for files because you only have one possible place to look for them. Early computers work this way, and some embedded systems still use a single level directory. But given your typical system is going to have like thousands, maybe millions of files, and you're going to have like several different places, you're going to have several different programs, you are gonna want to organize your files in some way, and we enter the hierarchical directory system. So we can think about it as one of two ways. A single user who wants to organize their files, or multiple users on the same system, and they all want to organize their files. Either way, we have a hierarchy of directories, and then those directories are more directories, or files. The use of directories is to, well, organize our files. Although it's more complex, this system provides a means of organizing files. And because of that, nearly all modern file systems are hierarchical. There are some other structures that are not mentioned in this book, but they are mentioned in a different book. I'll briefly describe them here. The first one is a two-level directory. It's not so much a single user has one extra level of directories, but rather multiple users who each are sharing the same system, and they each have a single level directory. That's what's going on with the two-level directory. So we have the master file directory, or the root directory for this, that has directories for each user. And within those directories are each user's files. At the very least, this isolates each user's files from each other user. However, it's still too restrictive if, one, we want to organize our files, and two, we want to share files between one another. So, the next step from that is, of course, going to be the multi-level directory, but that still doesn't solve the issue of how do we share files between one another. Sure, you can have two users have the same copy of the same file, but you'd be saving the same file twice. What if we could just take pointers from two different places in the directory and have them point to the same file? So that's what's going on in what is called an acyclic graph directory, where we can have two pointers to the same file. But, okay, let me talk about the advantages to this. To two users, it will look like two of the same file, but under the hood, there is only one file, but for two different users, they're just accessing the same exact file. That means if one user makes changes to the file, the other user is gonna immediately see those changes. And this is good for collaboration. However, it violates one of the properties of a tree data structure, and that is, every file must have a unique path to it. So this file that I've highlighted in purple here, it's called count, and we can access it from the dict directory, but we can also access it from the spell directory. So, there are two different ways to get to the same file. This is no longer a tree, this is a acyclic graph. Called so because there are no loops in our directory. We can become even more general than this, and this is called a general graph directory. So one of the issues of an acyclic graph structure is ensuring that there are no cycles. If we let go of that restriction, then we get a general graph directory. So now it's possible for us to have cycles in our graph, which makes it great for taking shortcuts from one directory to another, but it introduces a hiccup when we try to start searching through this directory. Let's say I want to find a file and I start at the root. Okay, so I go to the AVI file, and then I go to this book file here. It's pointing to AVI, but it's also pointing back to book, which points to AVI, but it's also pointing back to book. I'm stuck in a loop! So that's a problem that we have to resolve with trying to traverse through a general graph directory. If we write a search algorithm for a general graph directory, we ought to code it so that it doesn't get stuck in a loop. And that's because cycles are allowed to exist. In addition to having files that may have more than one path to it. As I said, searching for files becomes more complex because of that danger of getting stuck in a loop. And then we have what is called garbage collection. So if we delete a file, let's say we delete a file and it's called text. We just cut this pointer to it, and now that file is just dangling there, nothing is referencing it. So we need a garbage collector to scan everything in this directory. If it finds a file that has no references, then that is a file that can be deleted. What if we try to delete this unhex file here? So unhex is being pointed to from two different locations. So it's being pointed to from here, but it's also being pointed to from here. What does it mean to delete this file? Are we deleting this connection here, or are we deleting this connection here? Or are we deleting every connection? Here's where I have to explain the concept of linking. So to make these two different connections, we have to link. We have to create a link from one location to another location. And it's true that we can have two paths that refer to the same file. We can remove one of those paths by using a system call called unlink. That's the undo process. So if we have link and unlink, which is used to establish and remove connections so that we can have more than one path to the same file, if there is only one path left and we call unlink, that's going to be no different from deleting a file. If we call unlink and we specify a specific path, then we can that's going to have the effect of deleting one of the many existing paths. If there's more than one path and we delete one of them, and there's still more paths left, what unlink does is remove one of those possible paths. If there's only one path left and we delete that path, we unlink that path, then it's going to be identical to deleting a file. So that's enough on these other directory structures. I'm going to go back to our book right now, and I'm going to talk about path names. So I was talking about path names already, but let's go more in detail about it. When files are organized in a directory tree, we need a way to specify file names, and there are two ways to do this. The first one is to use the absolute file name, and that is the path needed to reach the file starting from the root. So you start at the root, which is the beginning of the entire directory tree data structure. You start from there, and you go from folder to subfolder to subfolder to subfolder until you reach your file. There is another way to do this, and that is called a relative file name. Basically, you have a program specify what directory you want to look at. Once you specify that directory, you pretend that directory is the root, and from here you work with shorter paths this way. So you don't have to specify a path that starts all the way at the root and goes to that directory, and then from that directory to your file. Rather, you start at that working directory and then work your way to that file. If a program only needs to work within one directory, then we can use relative path names. If a program has no idea which directory to work at, or it must change from directory to directory, then we're going to want to use absolute path names. So as I said, the absolute path describes the subfolders you need to enter to reach a file. And those file names are delimited using a / in Unix and a / in Windows. And in one older system, it's a greater than sign. That is the delimiter for multics, by the way. Absolute file paths always start at the root, and all files have a unique path, unless we're linked files. As I said, some programs start by specifying a working directory. If we do that, then specifying the path to that directory is no longer necessary. Suppose we have this screenshot here, which is just a screenshot from when I was playing Minecraft the other week. It's got a very long absolute path, and this is it right here. e/user/ all the way to aldomods 10-atm10 /screenshots /2025-04-01 _23.49.55.png. That's a long file name, isn't it? Let's say, for example, I have an image editing program, and I tell that program to open the folder screenshots, specified by the same path here. So if I am to work with this program, it's working with relative paths, so if I try to access that same file as before, I don't have to specify the whole dang thing anymore. The path for the file just becomes this file name here. Because I'm starting in the screenshots folder, all I have to do is just go to that file. If a program knows which folder to work in, then we can use relative paths. If it's not known what folder the program will be working in, then we should use absolute paths. If you want to be absolutely unambiguous, such as, for example, I copy this folder to my desktop. Now I have two copies of the same file, but I want to tell which one is which, so I don't accidentally edit the wrong one. I would need absolute paths for that. Most operating systems that support a hierarchical directory have two special entries, dot and dot dot. Dot refers to the current directory, dot dot refers to the current directory's parent directory, or if we are in the root directory, it's going to refer to itself. If you're familiar with Unix, you might be familiar with the cd command. That is the change directory command. If you type in cd dot dot, what that does is it changes the terminal's current directory to be the parent of that directory. And then we can type in cd dot dot again to go back one folder again. And cd dot dot again to go back another folder. There are also system calls for managing directories. They are more varied and complex compared to the ones for working with files. These are the ones for Unix systems. There are more calls than these, but these are just the most important ones. Create creates a new directory, which contains nothing but dot and dot dot. Delete deletes a directory, but only if it contains no files apart from dot and dot dot. Open directory, which opens a directory, such as listing out the files inside. Close directory, closes the directory, of course. Read directory returns the next entry in an open directory in a standard format regardless of what directory structure is used. Rename renames the directory. Link makes a file appear in more than one directory. By specifying a existing file and a path name, we can create another link to the same file. So we can have two paths that lead to the same file. This is sometimes called a hard link, and unlink is the undo operation for that. It removes a directory entry. If the file being unlinked is present in more than one directory, only the path name specified is removed, leaving all other paths unaffected. If the file being unlinked is present in only one directory, then it has the same exact effect as deleting a file. Alright, so that's the end of section 4.2, and then we're going to look at section 4.3 after that. We'll see how far we can go with files and file systems, by the way. I said we would stop at 4.3, but let's see how far we can go based on what time we have. Because after files and file systems, we're going to look into deadlock and deadlock detection, deadlock prevention, and all that. So I'm going to leave it here. This is going to be the end of this week's video. We're going to hopefully conclude our discussion on files and file systems next week so that we can finally begin our last big topic in our course, deadlock. Okay. Have a good week. Finish up your project 2, and we'll come back next week to discuss more on file systems. Okay? Alright, have a good one, and see you next week. Bye.